Here's a question for you. Why does this query executes within an instant, while this one takes well over 2 seconds? If you said anything other than this rtrim method, congratulations, you have successfully failed. If you said that this rtrim method is the reason for this slow query, keep watching. We are going to find out if you are correct soon enough. We are going to learn how this and many similar problems are created by indexes. And we are going to understand exactly why they are created and how to fix them without dropping your indexes or sacrificing your query's performance. Most tutorials skip indexes. Beyond indexes make your query faster. We are going to learn how indexes work, what they are, and why they can actually make your queries slower. So, what exactly are indexes? Let's consider that this is a table in database. The database is going to create a main page called IAM page, which contains a variety of different pages. And pages are simply the smallest unit of physical storage the database can use to store something. Let's consider that you have a products table. When you insert a new product, the database is going to create some areas. It's going to allocate a section of memory on your hard disk and it's going to store your product there. Let's consider that your product need around 1 kilobyte of space, but database cannot allocate 1 kilobyte. It's going to always allocate one page, and the size of that page depends on the database. For SQL Server, it's generally 8 kilobytes. Therefore, SQL Server is going to allocate 8 kilobytes for your first product, and the next 7 products are going to fit within the same page. In reality, a single page can contain over 200 products at once, unless you're storing images in the database, which I don't recommend doing. Don't do that. But let's consider that this is a page and this is going to contain a variety of different products that we have inserted. And these products are not going to be in sequence. You might have product 1 there, product 2 there, product 3 there, and after product 3 you might have product 18, product 16, etc. And you might have product 4 somewhere around here. And this happens because database is looking for the most optimized way to put your product within the hard disk. It's going to look for a page that's free. It's going to look for somewhere to put your data in. You might delete product number 3, and when a new product like product number 200 comes in, it's going to take the space of that product number 3 and put the product number 200 there. And therefore, the resulting structure will be very messy and unorganized. And it's going to look a bit like this. In reality, SQL Server doesn't work like that, but I'm going to keep that simple. And this structure is called a heap, which is basically just consider that a heap, everything is lying around, nothing is organized, and you might have your product number 1 in the first page, product number 2 in the 18th page, and then product number 3 in the second page, and everything is just chaos. So what indexes does is they create an organized table from which your database can find a product fast. So here we have an example index, and the way this index works is that the database, let's consider that it's looking for the ID number 3. I know I have horrible drawing skills, but just consider that I am doing ID number 3. The database is going to come here, and from here it's going to find out if ID number 3 is to the left or it's to the right. How this finding happens, we are going to talk about that later. but it finds that the ID number 3 occurs on the left side. So it goes left. Now we find the same thing again, which is left once more. So we go left again, and then we go left again, and we find this area, this 1 to 25, where ID number 3 is lying. And it doesn't actually contain our product. Remember, our product is somewhere around here. It's in our second page, but within our index, we have an address, something called a raw locator that points to our page number 3, and therefore from here we can directly jump to page number 3 and pick our ID. On the other hand, if we are doing the same thing without an index, we would begin here, and here we would start looking for an ID number 3. From the ID number 3, we are going to look at all the products in this area. We are going to determine no, ID number 3 is not here, and then we are going to go to the second child and then look for ID number 3 here. And this is a long process. By using an index, we can directly find out that ID number 3 is here. We are going to jump to that exact page, jump to that exact row, and find the ID number 3 in only 1, 2, 3, 4, 5 steps. The fifth step is actually extracting the ID from our heap. Now let's consider that we are trying to find ID number 3 to 28. Now we can take the same step. We can find ID number 3 here, and we know that ID number 3, 4, 5, 6, all of them appears in the sequence within the same page. So we start looking, we read all the way to ID number 25, and after 25 we have those links around each page. As you can note, we have arrows between them, and using those arrows we can go to the next page and then just start reading 26, 27, 28. We have all our products, we stop. And then we pick all of these raw locators, all of these locators or indexes or addresses that we have to a heap table. We go back to the heap, and then we start picking these products one by one, and we can find those products much faster than if we would have been looking at every page one by one. Now let's go back to SQL Server and do some practical work. I am going to begin by expanding my table within SQL Server, and I am going to consider that you understand about SQL Server, queries, tables, etc. already. Otherwise, indexes aren't going to help you. Go learn some SQL first. We are going to go to indexes here, and from here I am going to right click, select new index, and select new non-clustered index. There are multiple options here. We are not going to talk about all of them right now. For now, let's stick with non-clustered indexes. Here I am going to add two columns. There would be two columns that we would be able to search with. The first one would be status and the second one would be created at. Let's click OK. OK again. It might take a few seconds for index to be created. And it's created. Now we can use it in a query. We have added status and created that, therefore we are going to use status within a query. Let's try something like select static from orders where status equals to pending. Let's hit F5, and it takes about 4 seconds to execute because of the number of rows. But we are not going to focus on the execution time right now. Instead, we are going to focus on the execution plan. And you should be able to find a button like this called include actual execution plan, or you can just select the query or hit Control M. So after pressing Control M or this button, we are going to run the query again, and this time a new tab is going to pop up here. There we go. And here you can note a few points. Most importantly, you will note that we have a clustered index here. And SQL Server doesn't have heap tables. It does have heap tables, but most of the time it avoids heap tables and use something called an index organized table. We are going to talk about that later. It's difficult as it is. But to put simply, SQL Server isn't using a index. And we can try adding another filter. Let me explain why it's not using an index later. But let's try something simple like 230101 and 2023 0131. Run again. And this time you will note that we have an index seek non-clustered. In SQL Server, you have a main index called clustered. That's your primary key, that's your ID. If you see a clustered index seek or a clustered index scan, SQL Server is going back to your table and using that table to fetch the data. This time we have something called a non-clustered index seek. You can see the name here, non-clustered index seek, which means that it's using an index apart from our primary key index, our clustered index. And by this seek here, it has two keywords, index seek and index scan. If it's using an index seek, that means that it's using shortcuts like I have shown previously by going to the exact table and then reading from there. Instead, if you see an index scan, it's reading the entire table. Even though it's using that index, it's still reading every single page within that index. It's not using a shortcut. So it's using an index seek here, and if I hover on that, you can note that we have a seek predicate, and I cannot hover on that because the pop is going to disappear obviously. But just look at that and you're going to note that we have two predicates. We have status equals to pending, and we have created at is greater than equals to this and created at is smaller than equals to this. And if we come back here, we have a key lookup clustered. So what's happening here? Basically, this is performing the exact process that I defined. It's using the status first to find the page, then it's using created at to find the exact pages within that created at range. SQL Server can use multiple columns within an index if you apply the filter correctly. So it's first using a status and then using a created at. And once it has all the raw locators, remember that we don't have the complete order here. We just have a raw locator. So it goes back, and then after going back, it's going to apply a key lookup. It's going to find that exact ID, that exact value here, and then use that to find the product. And finally, after finding the product, it can join them together. If you see here, it's performing an inner join, even though we don't have an inner join here, because it's selecting for our index and then it's joining it with our main table, not our heap. SQL Server doesn't have heaps, but our main index organized table, our clustered index, and then it's combining that into our select. So it might seem a bit complicated. So let me make it a bit more complicated. Obviously, I am going to remove the static, add order ID, status, and created at. And this time our execution plan will become a lot more interesting. Let's press F5 again, and you will note that this is much faster. And if I go back here, you will note that we have a single operation, a single index seek, and in other words, we are finding everything from here. We aren't even going back there. And the reason this happens was because SQL Server has something called included columns. Included columns are columns that are stored directly within this leaf node, these last nodes here, and it's stored with your raw locator. If the entire data can be found directly within that page, SQL Server will never have to go back to that heap table. It will never go to heap table and say, hey heap table, give me that product number 3. And since it finds the entire data here, it can be much faster since it no longer has to go back and perform all these joins. So to go back here, we have used order ID. And your primary key, your ID, is always stored within your non-clustered index. But we can actually make our static faster by going back to our index. And what I'm going to do is that I'm going to go to included columns, and here I'm going to add customer ID and amount. And note that we don't actually have to add order ID here. Order ID is always added within our index. If I click OK now, click OK again, the index is going to be recreated, which takes a few seconds once more. And now if I execute the query again, it's going to give us an index seek with a predicate, And there we go. It uses a seek predicate perfectly. Now, before we wrap this up, I'm going to tell you 3 common pitfalls that most developers run into, and will tell you how to address any of those. Now, before we wrap this up, I'm going to tell you 3 common issues with indexes that most developers should be aware of. So let's consider this query. It seems pretty simple, and it seems like that our status index will be used in this case. So if we use our execution plan, I'm going to enable the execution plan here and then run the query once more. And within the execution plan, we can see that our index is used. But if I hover over that, you can see that it's using a predicate and not a seek predicate. And basically, a predicate means that SQL Server is applying a where clause. It's not using an index, it's scanning every row to find the rows which matches. On the other hand, if we have a seek predicate, that means that our index is being used. In SQL Server, any function is a black box to the query plan maker or query optimizer. If I call a function here called black box, and that black box method is going to convert a SQL to uppercase, this is going to this might seem obvious to us, but for SQL Server it's a black box. It has no idea what upper method is doing, and therefore it cannot apply an index. So if I remove that, I am going to copy the query, remove the method, and call that once more. And as you can note, our query has become faster, and within our execution plan, it's using a seek predicate instead of a predicate. And you might ask what to do if we actually need to use a function. Well, first of all, if that function is null, don't. You need to do status is null or status equals to empty string instead of this is null status empty string equals to empty string, which you might have seen in many code bases. Use an or clause, the column is null or the column is empty instead of this is null. But if you do need to use a function, you can use computed columns. I'm not gonna go into detail. If you need to, you can ask ChatGPT. The second pitfall that we need to talk about is index ordering or column ordering within an index. Let us move that to an older territory so we can get some data here. And within our execution plan, you can note that it's using our index, but it's using a predicate once more. even though we have an index on created at, and it should use that index, we aren't using any function, we aren't applying anything that should prevent this index from being used. Well, the reason is that within an index, if you have more than one column, one index is a single B tree. And a single B tree means that it can be ordered in only one way. It's going to order by your first column, then your second column, then your third column, and so on. If you have 5 columns and you don't use the first column and then add the remaining 4 filter clauses within this index, within your filter, it's still going to skip the index completely and use an scan because it needs the first column to perform the seek. So if we go here, let us go to our indexes here, and here we can see that its status appears before created at. If we move them around, created at will be filtered, but only status filter will not work. So let us go back and try adding a status filter in its place. If I do status equals to pending and then run the query once more, our execution plan is using a seek predicate. And how to remedy that? Well, you need to, if you have a single index, don't add 3 or 4 columns there. Instead, create separate indexes. It doesn't mean obviously that you need to index every single column, because remember, every index is just a redundant B tree. Every time you add an index, SQL Server has more storage to maintain. Every insert query has to update more trees, and therefore every index means slower insert queries. But if you do need to filter on 2 columns separately, use 2 separate indexes. Don't use a single index. If we go back here, if we create a separate index on created at, we would be able to filter on created at as well as both status and created at without issues. How this both works is another story. Let's leave that for another time. Finally, we have another familiar looking query which uses the like operator. And what do you think? Is it going to use the index? Well, if I execute that, and you guessed it, the index isn't used, instead the predicate is used here. And the reason is very interesting. The reason is because of this percent sign here. If I remove that and leave that percent sign here and then press F5, it works. And this time you will note that we have 2 different attributes here. We have a predicate which is same as before, status like pending, and then we have a set seek predicate which is basically order status starts with pending, which is much faster than scanning every row. And this is because SQL Server can find, by ordering the B tree, it can find all values where status starts with PEN, for example. So if I put PEN here and then press F5, it's still going to be much faster than adding like %PEN or maybe %pending. Just PEN starting with this will be much faster. And addressing this is very subjective. You can just choose to place a single percentage mark at the end. If you place a single white card at the end, this is going to filter and index properly. Or you can choose to use a full text search engine. A full text search engine might be overkill if you just need to search for customer names and similar, or it might be very practical if you're building a full blog and you need title search functionality. As always, go to ChatGPT, ask it the perfect use case, the perfect tool for your use case, and work it out yourself. But now that you know these three pitfalls, you should be aware of those and you would be able to apply those in your development every day to make your queries run faster.